Show by the principle of mathematical induction that for all n belonging to the set of natural number, n squared plus n is an even natural number. Now that means if n is a natural number, we need to show that n squared plus n is also a natural number and it has to be even. Okay, so what we'll do? We will first consider a statement. So let Pn be the statement, let P of n be the statement. We're going to name this statement actually. That's what we have to do. We're going to name this statement as Pn, which is n squared plus n is an even natural number. Fine. Now, this particular statement can be expressed as P of n. We use a colon, and after that we write the statement n squared plus n is an even natural number. Is an even natural number. Fine. We're going to label this as number 1. So we will check if this is true for the first natural number 1. So let n be equals to 1. Then we have P of 1 such that we have 1 squared plus 1. So that's going to give us 2. So this is true. So the 2 is an even number. So we say that the statement is true. So we write down the 2 is an even number, is an even natural number, is an even natural number, which means that the statement is true for n value equals to 1. This implies that P of n is true for the first natural number, which is E1. Now, if it is true for n equals to 1, it will be true for n equals to 2 as well. But we don't have to check for n equals to 2. We will go to the mth number. So we'll say that, we will say here that let P of m be also true. P of m be also true, where m is a natural number. So we'll say m belongs to the set of natural numbers. Fine. Now, what does P of m stands for? P of m is simply the statement. All we have to do is replace the n with m, so we'll get m squared plus m is an even natural number. So it's an even natural number. Now, our goal will be to use this statement that P of m, where m squared plus m is an even natural number, we'll use this statement to show that P of m plus 1, that is also a true statement. Fine. Now, since m squared plus m is an even natural number, so this simply implies that m squared plus m, this can be expressed as 2 times some natural number k, where we are considering k to be some natural number n. But since it's an even natural number, we've already mentioned we can always say that m squared plus m can be expressed as an even multiple of some constant k or some natural number k. Fine. Now what we'll do, we're going to do some manipulation here. And what we will do here, to the first term m squared, we're going to add 2 terms. We're going to add 2m plus 1. Now this is an extra term that we are adding, so we need to subtract it as well. So what we're going to do is subtract 2m plus 1. All we have to do is add those 2 terms to the right hand side, and then we have the second term, which is m. But what we'll do here, we're going to add a term which is m, which is 1 to it, and 1 being an extra term, so we have to subtract it as well. The reason why we have done this, because m squared plus 2m plus 1, what is it? This is simply m plus 1 whole square. When we complete the square, this is what we get. This will be added to m plus 1 equals to, now what we have here is 2k plus 2m, so 1 plus 1, that will be 2, which means that each of the terms is going to, there will be a total of 3 terms, and they will have, each of them have a factor of 2. So we can pull out that factor to get 2 times k plus m plus 1. Now k and m, these are already natural numbers. So which means that if we add 2 natural numbers and add 1 to it, it's still going to be a natural number. So instead of expressing it as 2 times k plus m plus n, we can express it as 2 times lambda, where again lambda is a natural number, which is k plus m plus 1. And we have lambda belonging to the set of natural numbers. Now what we have done here is we have expressed m plus 1 whole squared plus m plus 1 as a even multiple of some natural number lambda. This simply tells us, that m plus 1 whole squared plus m plus 1 is an even natural number, is an even natural number. Now, if this is an even natural number, this proves a statement. This simply tells us that P of m plus 1. Now what was P of m? So we considered P of m to be m squared plus m, which was already true. Now P of m plus 1, we were able to show that in place of m, and the first term and the second term we have to replace with m plus 1. So the statement m plus 1 whole squared plus m plus 1 is an even natural number. It is an even natural number. So now we have generalized and said that hence we can say that the original statement P of n such that n squared plus n is an even natural number, This particular statement is true for all values of n belonging to the set of natural numbers. In other words, we are saying that pick up any natural number n, this particular statement n squared plus n is always going to be an even natural number. We can verify that, although this has verified it. So let's say we take n to be equals to 31. So if we take n to be equals to 31, then P of 31 is simply going to be 31 squared added to 31. So we can take 31 as the common factor. So 31 added to 1. So this is simply going to be equals to 31 times 32. Now we know that 32 is an even number. We have an odd number 31 multiplied to an even number 32, which is going to yield an even number, and we have showed it, and it's going to be a natural number. So we have showed it for P of 31, which means for n value equals to 31, we are going to get an even natural number. So this is how we can show that a given statement is true with the help of the principle of mathematical induction.